Welcome back. This is the second lesson recording for IM1, October 13th, 2020. So we've just finished the Desmos exercise to card number 10, where we've explored the hand clapping record from Brian and from the record holder. So what are the takeaways? You are going to take notes on this. This will summarize what we've come up with. So when you are comparing two different sets of data, if you convert it to a unit rate, then it's really easy to compare who has more. So in Brian's case, we had 62 claps per 4.5 seconds. That means the unit rate is 13.8 claps per second. Okay, in contrast, the record holder was 721 claps per 60 seconds, so the unit rate is 12.0 claps per second. Okay, so obviously you can see that 13.8 is bigger than 12.0. That means Brian clapped in 1 second more claps than the record holder. So yes, he's going to break the record. Now the input X represents the time. That's the independent variable. That was the X-axis. And the Y-axis was the output, which represents the Y, which was the number of claps. And that's the dependent variable. Now slope of the graph, or M, was 13.8. Okay, 13.8 really represents 13.8 claps each second. That's the 13.8 claps per second. We sometimes also call the slope rate of change or growth rate for that reason, because it is the unit rate we're talking about. So that means when X changes by 1, how much does the Y change? And that's the slope. Okay, so the Y value, the output changes by 13.8 every time X changes by 1. That's what a slope is. Now Y-intercept, or B value, was 0. Okay, and because at the time 0, number of claps were 0. You're starting off with 0 claps in the beginning, and then you are building them up. So that means the equation for representing the situation is Y is equal to 13.8. The slope is the number that is being multiplied to X, and then plus the Y-intercept plus 0 should be here. But plus anything plus 0 is just that anything here. So we're not even going to bother writing that. Okay, so if you do not see if you do not see a number being added, you can always say it's plus 0 and the Y-intercept is 0. Okay, let's move on to our next video, next situation, and explore this one. So this is candle burning situation. Watch this video. Okay, so as the time goes, the candle is getting shorter and shorter and shorter. Okay, thankfully there's no burning danger here because it's just going to melt onto the gradient counter. Here we go. So eventually it is no longer. Okay, the height is 0. So now, given the situation, you're going to be asking this question: when will the candle be completely burnt out? And you're going to complete card number 11 to card number 12 of Desmos. Right now, pause the video, please. Okay, so this is card number 11 of Desmos. This is where you are just making some notes on what you've noticed or what you've wondered by watching the video. And then second one, what is your estimate in minutes? How long it will take for a candle to completely burn out? Okay, just spend 10-20 seconds thinking about that and fill it out. Okay, so when I watched the video, I couldn't tell when it was going to burn out completely because I had no reference of time. So here we go. We have a little bit more information this time. So we're starting with 17 centimeters height of the candle, and there is the timer. And 15 centimeters at 24 minutes, 14 centimeters at 50 minutes, 13 centimeters at 76 minutes, 12 centimeters at 105 minutes. And 9.5 centimeters at 156 minutes. So now that you have more information, you're going to move on to card number 13 and 14 of Desmos. Please pause the video and go ahead. Okay, so they've actually put the data that we found on the table, and then from here they've plotted it over here. And you can see that the graph actually looks like a straight line. It's not a perfectly straight line, and there's a reason for that, but generally it looks like a straight line. So we want to know how long it takes for the candle to burn out. That means when it burns out, what is the height? When does it burn out? The height is going to be 0, right? When is this graph going to reach 0? So I could have a better estimate using this graph and maybe extending this, eyeballing it, maybe saying, oh, okay, maybe about 340, something like that. It would be helpful if I had a straight ruler, wouldn't it? Okay, or if I could, or you might have used the table and said, okay, I can calculate the unit rate by collecting few of the points and figuring out that way and calculate that way. Okay, so that was up to you. And then card number 14. We will model the candle burning as a linear equation to help us refine our estimate. This means we have to figure out two pieces of information. That's the slope and the y-intercept. Okay, the slope is the rate of change in the situation, and y-intercept is the starting value of the situation. So what does the slope represent in this situation? What does y-intercept represent in this situation? Well, slope represents the rate of change. But what is the rate of change in this situation? It's how fast the candle is melting, how fast the candle height is decreasing by, right? So slope actually represents how much the candle height decreases in. Now, we're always going to be looking for unit rate. So what is the unit of the x-axis? It's 1 minute. So it's going to be 1 minute. Okay, so in 1 minute, how much the candle height decrease in 1 minute? It's decreasing because it's going down. And what does the y-intercept represent? What does this point represent? At time 0, how tall was the candle? It was 17 centimeters. Okay, so how tall the candle was in the beginning. In the beginning, and which was 17 centimeters. Okay, so then I can go, okay, so then, all right, so that was card 13 and 14. Now let's go back and recap some of the things that we discovered. Okay, so the burning candle, if you are representing as y is equal to mx plus b, because we see it as being a linear equation or linear graph, so input x represents the time. That's the independent variable. What about y? The output y represents the height of the candle. Okay, that's the dependent variable. And it's linear. We think the height of the candle decreased by a fixed amount each time. When we actually saw the graph, it looked like a straight line too, didn't it? Okay, so remember, linear means a straight line. So y-intercept, it represents the height of the candle at start, which is time is when time is equal to 0, which was that b was 17 centimeters. What about slope? The slope represents how much the candle height changes each minute. So m is, well, we don't know. That's what we need to figure out. So how are we going to figure that out? First of all, is the slope going to be positive or negative? Okay, looking at the graph, did it slope downwards or did it slope upwards from left to right? Okay, so is it going to, remember, puff positive, nice negative, this 0 fun, and undefined. So it's going to be negative. It's sloping downwards. It's a negative slope. And if you look at the table, okay, so for 24 minutes, the height goes down by 2 centimeters. So first 24 minutes, the height decreases by 2 centimeters. That means the height change for each minute is going to be 2 centimeters, and it's negative because it's going down by 24 minutes. Okay, so that is approximately negative 0.08 centimeters per minute. Okay. So the reasonable equation from what we figured out is that we found the b to be 17. So we found the slope to be negative 0.08. So put it together, y is equal to negative 0.08x plus 17. Remember, this number, the slope, is being multiplied to x. It's not being added. It's being multiplied to x, and that is the number right in front of x because that's being multiplied to x. Okay, now you're going to pause the video and go on to card number 15 to 16. Okay, so as a class, we used the first two data points and found the slope to be negative 0.08. So if you actually graph this on this, it's the red line. Now, does it look like it's going through all the points? It's not a very good representation. And if you remember the candle actually had that sort of pointy shape. And that is the reason it was a little faster in the beginning, because it had much less wax to begin with. And then it became more stable. So this is not a very good representation of the decline or the change in the rate. So what can we change these to? Okay, so if you change, it's asking us to change this to 0.05. And if I change this to 0.05, negative 0.05, that looks much better. Okay, that's a better fit of all the data points. Okay, so then I can submit, and then next, from here, what will be my prediction as to how long it would take? So my prediction will be, when the height is 0, it will be about 340 seconds or minutes. 340 minutes. Okay. Okay, so let's review the result. Okay, I've actually fast forward double time so that we can actually see the result before the recording ends. So here we go. All right, so if they are actually graphing this alongside, and that's the graph that we saw.